Hi everyone. This lesson is on nth root functions, and by nth root, that's really just kind of a stand-in for, any number that we want to use. So cube root, square root, fifth root, whatever. Okay. This lesson is really kind of a hodgepodge review of some things that you did back in Algebra 1. So a lot of this should sound familiar to you. Starting with this definition of nth root, x is considered an nth root of k if and only if x to the power of n equals k. I know that sounds confusing, but if I were to write this thing out here, x is an nth root of k, really what that means is if I do the nth root of k and get x, that means that this thing here must be true, that x to the power of n equals k. All right, that these two things are kind of saying the same thing. All right. As a more specific example, we know that the cube root of 8 is equal to 2. That's because 2 to the third power is equal to 8. That's really what this thing is talking about, is that that's what it means to be a root of something, is that when you raise it back to that power, you get the number that you started with. Okay? So one of the big things that comes up with this material is this difference between when n is an odd number and n is an even number. And we're going to talk about that difference in the context of this expression and this expression. Okay, so we're going to kind of write down when x is even, when x is odd, what happens. Starting off with this kind of way of writing the expression. If I look at the function y equals x to the power of n, and n is an odd number, just as a reminder, the graph of something like that is going to look like this. This is what's called an odd power function. Okay, the graph will look like that. And what that means is if I plug a number in there for y, or like a number in here for k, if I'm looking for a solution for this thing, no matter where I go, there's always going to be one solution, right? If I go here, I have a solution. If I go here, I have a solution. Okay, so anytime I have an odd exponent here, and I'm looking for, a specific value of y, or I'm looking for that root of whatever that k value is, I'm always going to have one answer. So let's see. If I'm doing the nth root of k, like what's written above, this will always have one solution. Always. And the reason we're making a big deal out of that is because that's going to contrast with what's happening over here. Okay? If I do this same thing with an even power function, y equals x to the power of n, then if you recall, this is going to look more like a parabola. Technically, it's not supposed to be called a parabola unless it's an x squared. Okay? So if it was like x to the fourth, x to the sixth, and so on, that's not technically a parabola, but it still has this shape to it. Okay? And so if I were to say, I want the nth root of a positive number, if I want my k value to be a positive number here, if I go up to where these numbers are positive, I have two solutions, right? But if I go down here to where things are negative, I have no solutions, all right, because this does not cross over into the negative territory. So when I do the nth root of k, and we're talking about even values for k, if k is positive, I will have one solution. Nope, sorry, two solutions, I just said. Okay, so really these pink lines kind of represent that k value. Okay, so when k is positive, I will have two solutions. But when k is negative, I will have no solutions. Another way of saying this is basically that we can't take even roots of negative numbers. Okay, we can't take square roots of negatives. We can't take fourth roots of negatives. And so I may even just kind of jot that in here. That really that's the point we're trying to drive home here, that we can't take even roots of negative numbers. Okay, and you knew that. You knew we can't take a fourth root of negative whatever. We can't take a sixth root of negative 36, anything like that. Okay? Okay, one more reminder is that we're going to be talking about roots, but we're also going to be talking about what's called rational exponents. Rational exponents are fraction exponents. And so what I want you to know there is that if I'm doing the nth root of x, that's the same thing as doing x to the power of 1 over n. Okay? So once again, using my example from above with the 2 and the 3 and the 8, the cube root of 8, that's the same thing as me saying 8 to the 1/3 power. That a root is the same thing as an exponent with that number as a denominator. Okay? We should also note that if this x were to have an exponent on it, let's see, so if we were to do like the nth root of x to the power of a, for example, that would be equal to x to the power of a over n. Okay, so if you've got an exponent on the inside here, you can put these two things back together as a fraction and make it a over the power of n. Okay, and again, that should be a throwback to Algebra 1. All of that should sound familiar to you. This is all of this is kind of just reminders of stuff that you already know. Okay, so let's talk about this example 1, and let's talk about what not to do to answer this question. So it says, show that 1.5 is a cube root of 3.375. If we're trying to justify this mathematically, we need to have something to fall back on. And so it's not enough for us just to say, well, I typed the cube root of 3.375 into my calculator, and this is what I got. For a couple of reasons. One, if it's one of these situations where there's two solutions, your calculator's only going to give you one of them. And secondly, if we're going to try to justify ourselves with this definition of what it means to be a cube root, we have to kind of follow this format to be able to use that definition appropriately. So if 1.5 were a cube root of 3.375, then it should be true that 1.5 cubed would give me 3.375. So the way I would justify this is I would say, hey, look, when I do 1.5 cubed, it gives me 3.375. Okay, this right here would be my justification or my showing you that this works out. Kind of like I did up here. I showed you that 2 is the cube root of 8 because 2 to the 3rd power makes 8. I didn't pull out my calculator and say, hey, look, when I do the cube root of 8, I get 2. All right, that's not showing you that something is true. So for this one, negative 1.5, I'm going to do the exact same thing. I'm going to take that negative 1.5 and cube it. And you should understand that because this is negative and I'm raising it to an odd power, my answer is going to come out negative. So it's going to come out to be negative 3.375. And then I would just take a minute to point out that that's not this number, right? That's not 3.375. Okay, it came out negative because of the negative on their original. So this right here would be how I would show that. So that would be my final justification. Okay, let's hop to a couple more examples here. Evaluate each of the following without a calculator. There is going to be a portion later in this chapter where I ask you to do a bunch of this stuff without a calculator. You'll have a no calculator quiz. I think you can handle it. I'm not going to give you any numbers that are unreasonable. So if I'm looking at this 1/8 to the power of 1/3, just remember that that's really like 1 to the 1/3 power and 8 to the 1/3 power. Okay? 1 to the 1/3 power is 1, because 1 to any power is 1. And remember, this really means the cube root of 8. Now, realistically, I'm expecting that you know that one off the top of your head. Okay, and that's why I can say do this without a calculator. So 8 to the 1/3 power is 1/2. Let's say that you didn't know that one off the top of your head. Okay, you didn't know what 8 to the 1/3 power was. Here's a strategy for you. You can take that 8 and make a factor tree for it. So we can say, how do you multiply to make 8? Well, first thing that comes to my mind is 2 times 4. In fact, I think that's the only thing that comes to my mind. And then the 4 could break down to 2 times 2. And then do you notice how I ended up with 3 2's? Okay, so this means that 2 to the 3rd power equals 8. And then remember our definition of what it means to be a cube root. It's whatever to the power of 3 would equal that number. Okay, so that's how our answer comes out to be 2. So we could do something similar for that next one, the 4th root of 81. Again, my hope is eventually you'll get to the point where you would know that one off the top of your head. But if you didn't, we could go 81 and break it down into its factors. 81 is 9 times 9. And then 9 breaks down into 3s. So what I'm seeing there is 3 to the 4th power. So if 3 to the 4th power is 81, then the 4th root of 81 is 3. It's one of these pieces, okay, one of the 4 pieces. Okay, so that's kind of the process I would expect you to go through without a calculator. Obviously, if you knew this off the top of your head, if you knew that 3 to the 4th power was equal to 81, you wouldn't have to write all of this out. Okay, example 3. You may be able to think through these without using a visual. I'm going to draw a graph for each one of these to show you what, or why the solution is what it is. So if I'm looking at 4th roots of 1296, what I really want to think about is when does x to the 4th equal 1296? And so if I draw a picture of that, x to the 4th power, that's one of those even power functions, so it's going to look bowl-shaped or U-shaped. And 1296 is going to be somewhere way up here. So when I look at that graph, I see that this has 2 solutions. Okay? It has 2 places where it intersects. So I would say it has 2 4th roots. Okay, a positive and a negative. All right, how many real 5th roots does negative 1024 have? So I'm going to draw that arrow there. This next one will be right here. Again, what I'm asking myself is when does x to the 5th equal negative 1024? So x to the 5th, that's an odd power function. So that's going to look something like this. And if you think about where negative 1024 is, that's going to be somewhere way down here. And so no matter where this was, we were always going to have just one solution. Okay, so there would be one real 5th root. Okay. How many real 6th roots does negative 729 have? So we'll go down here with this one. Again, the question I'm asking myself is when does this happen? Okay, x to the 6th equals 729. That x to the 6th is back to an even power function, so it goes like this. But negative 729 is going to be down here somewhere. Okay, so this one has 0 real 6th roots. So just to kind of recap what we just found is because this was an even root of a positive number, we had 2 solutions, right? A positive and a negative. And so just real quick, let's figure out what the answer is. This question didn't ask us to do that, but so I'm doing 1296 to the power of 1/4, or the 4th root of 1296. Okay, so in my calculator, when I do the 4th root of 1296, I get 6. That means that 6 or negative 6 would work here. So I could do 6 to the power of 4, and that should give me 1296. I can also do negative 6 to the power of 4, and that would give me 1296. Sorry, I guess you can't see that very well. Kind of faded. But so that's why I have 2 solutions. Right? It is important to point out, you know what, I want to do this on a graphing calculator. If I wanted to do the 4th root of 1296 on my calculator here, just to remind you how to do that if you don't remember from last year, I would type the 4, okay? And then under the math menu, I'm looking for this one that looks like a root, but it's got an X there, okay? And when I choose that one, so that's option number 5, notice how the 4 got replaced with that little number in the corner. So really now I'm finding a 4th root of 1296. Notice that your calculator only gives you one of the possible answers. You have to know that because that's an even root, there's going to be 2 different possibilities, 6 or negative 6, because of what we just talked about. Okay? If I were to do the 5th root of negative 1024, and again, I do just want to emphasize that this question did not actually require you to find what the fifth root was. It just wanted to know how many there were. But I also wanted to review how to do these in the calculator and kind of drive this point home. I get negative 4 because negative 4 to the power of 5 is going to give me negative 1024. But I don't have a second solution. I don't have a positive one because regular 4 to the fifth power would not give me negative 1024. It's going to give me positive. So I only have one possible way to make a negative 1024. And that's true for any odd root. All right, when you're working with odd roots, positive goes with positive and negative goes with negative. For this one, x to the 6th equals negative 729. Look at what happens in your calculator. So 6, and then negative 729. And I get a non-real answer. I get an error. Okay, notice this question was asking specifically about real answers. Okay, so I'm not living in imaginary land. If I were to do the 6th root of just regular 729, I don't remember what that is off the top of my head. 3, okay. 3 to the 6th power would give me positive 729. And negative 3 to the 6th power would give me positive 729 because an even number of negatives all cancel each other out. So that's why this doesn't have a solution, because both positive 3 and negative 3, if I were to do them to the power of 6, would give me a positive 729. I have no way to make a negative with an even number of factors. Okay? So justify that any way you want. Hopefully the pictures make sense to you for why that works the way it does. But that's really what we want you to see, is that even roots, so like this one and this one, even roots, if it's a positive number, you're going to have 2. If it's a negative number, you're going to have 0. Odd roots with positive or negative numbers, because even if I had a positive up here, I would always only have one solution. Okay. One more quick one here. Example 4, looking at these functions, x to the 1/2 and x to the 1/5. Which would you expect to yield larger output values? Okay. Well, I hoped that you would say this one is going to be larger, because you're only splitting it down into 2 pieces instead of splitting it into 5 pieces, right? But there is something kind of interesting that happens. Graph both functions on the coordinate plane. When is f larger and when is g larger? And so I'm going to take, so I'm still looking at example 4 from your notes here. I'm looking at f of x equals x to the power of 1/2. And what was my other one? G of x equals x to the power of 1/5. Okay. I should point out that this function here, x to the power of 1/5, even though your calculator or Desmos or whatever graphs the second half of the function, we really typically kind of disregard. We put a domain restriction on this so that we don't worry about these negative values, because this is one of those situations where like negatives would work for this one, but they wouldn't work for this one. Depending on what my numerator was, those negatives might behave differently. So we typically only consider kind of the right side of these graphs when we're looking at them. Okay, thought I should point that out. So we said we thought this x to the 1/2, so the red one we thought would always be larger, right? And that's what we see for the most part. But do you see that for this section of the graph between 0 and 1, actually this one is larger? So this area of numbers between 0 and 1, if you think about your fractions and decimals, they always are going to kind of behave differently than what you think they would, okay? When we're working with powers and exponents. Because when you take a fraction or a decimal and you raise it to an exponent, it actually gets smaller rather than larger. Okay, and so something we would think that would make your number larger will actually make it smaller. So when I look at that question on your notes, let me just get back to that here quick. Okay, when is function f larger? When is function g larger? I would say f of x is larger everywhere beyond 1. Okay, everything bigger than 1. G of x is larger for that little twilight zone area between 0 and 1. And you should also notice here that, when I look back at this graph, that at 0 and at 1, they're exactly equal to each other, okay? Every single one of these functions is going to contain those points 0, 0, and 1, 1. By the way, that would also be true if we looked at like, x to the third power. Anything with an exponent in it, x to any power, whether it be fraction or whole number or whatever, is going to contain these points 0, 0, and 1, 1, okay? Because 0 to any power is 0, 1 to any power is 1. Okay, so just back to your notes quick again. I would make a note of that. And really what we want you to see here is that this area, this set of x's, makes weird things happen with exponents. It makes everything work kind of backwards from what you think it would. Okay? And you can always check that on the calculator, but this would always be the area that I'm kind of targeting when I'm looking at where is it larger and where is it smaller. Okay, that was really it. Like I said, I don't think there was a whole lot of new there, other than maybe just some new ways of looking at things that you already knew about. But hopefully that should be enough to get you going on the homework, which is lesson 6-1.